non-uniform families of poly-size finite automata. Yeah, we are running a little bit behind schedule. Okay.
Well, thank you very much for the introduction. Okay, so this is the talk about in the field of the structural complexity theory. So I'm not quite sure how many people are really kind of good background about the structural part of the complexity theory. So but then the content of the talk is based on finite automata, so that everybody understands what I'm talking about. Okay, so this is the outline of my talk. Basically, this is about the automata, finite automata, but then I'm using the family of the finite automata. So that's a little bit different from standard situation. And also, I'm using the counting. So this is actually the notion I'm going to introduce later on. The most important thing is, as I said, the family of the automata. But then now, I'm also introducing the partial counting functions and the partial gap functions. I'm going to define those things in a few minutes. And also, we are considering the associated family of promise decision problems. So this is actually different from the languages. Okay, a sort of the extension of the languages or relaxation of the languages. And I'm going to show some inclusions and separations of the complexity classes based on those families of the promise problems. Okay, now I start with some bit of the background about this situation. So counting itself is one of the most important and intensively studied subject in computational complexity theory. Particularly counting means the counting down and accepting computation path of the non-deterministic computation. And for example, the permanent for the given integer square matrix n. So the complexity of this permanent is known to be the sharp P complete. Sharp P is the complexity class, consisting of the functions counting the number of accepting computation path. So this problem is really hard because the sharp P complete. So this, well, unless P is equal to NP, this function may not be computable. Okay, so we'll introduce the notation, two notations. The first one is the given machine. So in this case, the polynomial time non-deterministic Turing machine, NTM. So sharp M of x refer to the number of accepting computation path on this machine that take input x. Okay, but if you put the bar, so that we are counting the number of the rejected computation path. So if you actually just sum them up, you're actually counting the whole total number of the computation path. Okay, so now the counting function is the function that counts this sharp M of x. Okay, and the gap function is the function computing the gap between two values. So that the sharp M of x minus a sharp M bar of x. Okay, so the range of this function is, in this case, n, the natural numbers, including 0. And here, the gap function, the range of this function is integers. So we allow the negative values. Okay. So now the counting function, well, then this is just a historical bit of the historical background, but the variant to do with the notion of the counting function that we just discussed. The gap functions. So this is a little bit new. Fenner, Ortnell, and Kurtz, they introduced the notion of the gap functions. Basically, this is the gap between the two counting functions. Okay, so the variant introduced the complexity class called the sharp P. So this is the class of the counting functions. And the gap P is the class of the gap functions. So now we have now the name said this is a counting version of this is actually computing the gap. Okay, so we just keep in mind that those counting and gap functions possibly introduce a whole bunch of the complexity classes. For example, in the polynomial time level, NP that is also defined by the counting functions, and UP, C, quad P, sharp P, PP, and stoic P, SPP. And those complexity classes are actually defined, and particularly in NP and UP, probably P and parity P and PP. And those complexity classes are really well studied so far. But less one is here. Okay, in the logarithmic space version case, well, we have the similar notion here. L stands for the log space. So everything, you just simply replace the P by L, then you can get the log space version. Those are considered by those kind of guys, and much weaker one tape, linear time, non-deterministic Turing machine. So you only have one tape, read and write, and the time is bounded by the linear in the total length of the input. In this case, we have the similar one. The first letter one means one tape, and so on. The last lin means the linear time. Okay. All right. So those are the background somehow. Now, I'm going to start, the major part of this talk. First, I will introduce the non-uniform polynomial state complexity sort of theory. The Berman Lingus and Sokodas and Sipser, they started the notion of the discussion about the non-uniform families of finite automata, having only polynomial remaining inner states. Okay. So this is the families, not the single machine. Okay. Observe. And hypothesis, revise if you just look at the gap between those years, right? After the 70s, seem to be this notion has forgotten somehow. Then the hypothesis actually revitalized the study. He just brought in, we have this concept and we proved some new stuff kind of thing. And then I gave some extra work, the relativization, and I introduced more complexity classes. This talk introduced more complexity classes anyway. And also I talked about the pushdown case. All right. Now we go into the more details. State complexity usually refer to the number of the inner states for each individual machine. But now we have a family of finite automata. So the state complexity associated with this family is just a function. So you take the nth machine, then you can actually calculate the size of the total number of the inner states used for the nth machine. Okay, so this is the function. Right? Now the family of finite automata is said to have polynomial size if this state complexity function is upbounded by one particular polynomial. Okay, so I just keep using the word polynomial size. That means state complexity is bounded by polynomial. Okay, now we'll move on to the promise problem. Promise problem. Something more?
Yeah. Just I didn't notice because I didn't. Sorry, you forgot.
Oh, so the people did not see.
Yeah. But they heard it all. Sorry.
Oh, because there is an I kind of asking him to download the files directly into the computer, and I'm using the PowerPoint. Well, not many people actually using the PowerPoint slides. So probably that's the main reason.
No. It's just that we didn't share screen.
Is that okay?
Yeah, one.
Sure. Oh, okay, I can wait.
And sorry, I did.
No, that's
I
fine.
didn't notice. I was
about the promise problem. Promise problem is not a single set, but then a pair of sets. And those two sets have no intersection. And the first letter A, so this is a set of so-called accepted string or yes instances. The latter one, the R, is the set of the rejected strings or no instances. Okay. So the machine, this is a single machine. The machine is said to solve this promise problem if for all elements in 8, that means that all yes instances have to be accepted by n. Okay? And all instances in R, that means no instances, they have to be rejected by n. But we don't care about the other instances. Okay. Now, either yes instance or no instance. Those instances are called promise or valid. So we don't care about the invalid instances. We only care about the promise or valid instances. So that's slightly different from the standard language physics. Okay, now we will consider the family of those promise problems. Okay, now we just expand everything to families. The family of machines, in this case the finite automata, is said to solve this family of promise problems if and only if for any n, that nth machine solves the nth promise problem. So n matches. Okay. Alright. So now we're going to introduce the complexity classes. The 1D, 1n. The 1D is the class of families of promise problems that is solvable, that's solvable by family of polynomial size 1 DFA. So the 1 DFA means the one-way deterministic finite automata. Okay. And if you replace DFA by NFA, then we will get 1n. So the last letter stands for the machine type, the deterministic, non-deterministic. The first letter refers to the one-wayness. In this case, when I say the one-way, in this particular case, the head always moving, not stopping like making extra move. Okay. 2 to the 1D means instead of them using polynomial size, rho is an exponential size, similar to this. But we are not really considering the 2A case in this talk, but if we have a notion of the 2A complexity classes. Those complexity classes are not already defined in 70s, in the 4th and 60s. Okay, so just to show you just a bit of the information. So this is actually the kind of inclusion and separation situation right now. For example, 1D is different from 1n. 1n, for example, 2n is different from 2 to the 1d, for example. Right? And that thick arrow refers to the proper inclusion. So we have some 2 cases. Well, I'm not going to explain a whole bunch of things, but the Q stands for the quantum.
Can I just ask here, are there, among the inclusions, are there like open problems where you don't know if it's just a regular inclusion or a proper inclusion, or is this like...
But this is true, without any assumption, because this is one way.
Yeah.
Okay, but then the 2A case, and if you look at the 2A case, whole bunch of things is actually just we know the inclusion, no separation. So that's a tricky part.
Okay, but then you know that there is no separation, you know that you don't gain anything, it's not like... so all of this is like affirmative, it won't change. Yes, very good.
Okay, good. And P stands for the probabilistic. So we have a whole bunch of complexity classes. But then if you just look at the 1D and 1n, so we have several complexity classes in between 1D and 1n. For example, like this one, that we have some separation, but those dotted ones are not really known to be separation. Okay. Now we move on to the partial function. Partial function is the function. Okay, so before that, then I'm just show we are going to use the transducers to compute the functions. Okay, so we have an extra output tape. All right. but the head moves only one way in the stock. So now the partial function is a function from string to string, but then function have a predetermined domain. So within this domain, the value of f has some meaning. So that it is called, which is called defined. But then outside of D, even though f possibly outputs something, but that is not considered to be defined. So just think about it. Only a limited amount of the inputs, you have the values, but then outside of that, you don't care. Okay, so that's the partial function. Okay, now we clearly write, because the domain is associated with the partial functions, then we clearly write it down next to f. So this is the way we express the partial function. Okay, now we consider the family of the partial function. Okay, the given family of the one-way deterministic finite transducers compute this family of partial functions if only on domain x, domain D of D sub n, the nth machine, n sub n, take into x and I'll produce exactly this string on the output tape. Okay. Now, we encode, because we have to think about the counting function, the gap function, and the range of those functions are integers, natural numbers. So we will actually translate n into strings using binary notation, binary representation, something like this one here. And also, we encode the integer into strings using the preceding 0, 1, and 0, referring to the positive and negative. Okay. So just a bit of the trick we are going to use. So we will introduce the computable functions, family of the computable functions, partial functions. So 1f stands for the class of the families of the partial functions, computable by polynomial-size families of one-way deterministic finite transducers. And if you use the natural numbers or integers, then we will put the n and z to refer to what kind of functions we are talking about. Okay. Oh, so this is n, this is z. All right. So we'll introduce the complexity classes. The one sharp, that is actually this setting situation analog of sharp p. Okay. And also this is the gap, the analog of the gap p. The one sharp is the class, the collection of the families of partial functions, and computable by one-way non-deterministic finite automata in this particular way, so that you're just counting the total number of accepted computation path. Okay? The gap case is actually taking the difference between the number of accepted path and the number of the rejected paths. Okay. So if you restrict the outcome of the function not to be negative, then I put this subscript. So this is actually subclass of this one. Okay. So the situation is something like this one here. We have some separation, a clear separation between all the complexity classes we just discussed. Okay. Now we move on to the class of the promise decision problems. Well, we introduced the complexity classes. Those are actually corresponding to the polity P, UP, and okay. Those complexity classes are actually defined in terms of, here. For example, the one polity means we have the one sharp family of partial functions that actually produce either odd number or even number. Okay, so that's the meaning of the parities. And U means unique or unambiguous. That means the function output either 1 or 0, depending on the yes instance or no instance. Non-deterministic case, so we have already defined this notion, but this is actually characterized using one-shot families of partial functions, using the outcome of the function is either positive or 0. So this is total number of accepting paths. So either there is no accepting path, or we have some accepting path. So that's definitely defined 1n. Okay, so please remember this one. So 1u, so with outcome is either 1 or 0, and using one-shot families. Now we continue introducing the 3 more complexity classes defined by gap functions. Okay, so 1c equals is defined by the one gap function families, and using the outcome is either 0 or non-zero. And 1sb using the outcome of being 1 or 0. And 1p, so this is the unbounded probabilistic complexity class, and the outcome of function f is either positive or, sorry, I made a mistake. So this is a negative, non-positive, so that means either 0 or negative. Sorry, I made a mistake. Okay, so if you just focus on this one here, compared to the previous 1u, the only difference is, well, here is the same, 1, 0, right? Only difference is one gap. So if you just take the look at either one-shot function or a one-gap function, you actually define a completely different complexity class. Okay, so in this work, I proved the separations and inclusions of all complexity classes, something like this one here, right? And 1D and yn here, and so on. Okay, so we just added an extra machinery, that means the Push automata. So in Push automata, we can't use state complexity. We have to kind of elaborate in some other notion. So I defined the stack state complexity. Stack state complexity is the multiplication of the number of the inner states and this set. So the gamma is the stack alphabet. Okay, so stack alphabet is used up to e times. Okay, the e is the push size. Push size means in a single step, how many elements or how many symbols you actually put on top of the stack. Right? Because usually push automata is allowed to put multiple symbols into the stack. Okay, so 1DPD is the push automaton version of the 1D. So that instead of them using finite automata, we are using the here. Yes, one-way deterministic push automata. Okay, so this is actually non-deterministic version of it. All right, we are pretty much close to that. Okay. So this is the previously known result I just mentioned a few minutes ago, right? And associated with the push automata, we have those separations, the additional elements here. Okay. Now I finished presenting all the results. Now just to give you some bit of the open questions. There are a number of open questions, even though it looks like we have done already. But for example, one parity and one those two complexity classes, we don't know the relationship because I couldn't find the proof separating those things yet. Okay. Other thing is one sharp and one DPD, for example, right? And what about the 2A model case? example, then if you are thinking about it, so coordinate prove that 1n is different from 1d. But 2n versus 2d question is associated with L versus NL question. So we can't really solve that question somehow. So this is actually the question we don't know, but probably we need some kind of an assumption, or I'm not quite sure, because this is actually non-deterministic. This is the deterministic, even though we can use stack. But I'm not quite sure how we simulate those non-deterministic 2n lines. Okay, the last one will be, as I said, 2n model is really hard to analyze or showing the separation. Because it was the whole of the case, we need assumption, like L is different from NL in non-uniform setting, so to speak, right? So everything is really different. And also, this is slightly different from all the discussion we have so far. But there is the information, here's the information that, for example, P versus L or P versus NL question is associated with something like 2D and 2A. A stands for some alternating finite automata. So the finite automata, discussing the finite automata kind of resulting in something like P is different from NL and so kind of things. So this is I just stress on that finite automata seem to be so easy. A lot of people think, particularly people in the working on the polynomial time complexity practice, finite automata seem to be so easy, but it's not actually. Right? The really, discussing findings and the results associated with finite automata is a really good thing. Thank you very much.